You're watching a comet streak across the sky and thinking it's just ice and rock from the edge of our solar system. But what if everything we know about where comets come from is wrong? What if some of them aren't from our solar system at all? In 2023, astronomers spotted something that shouldn't exist, a comet so strange it's forcing us to rewrite the textbooks. Its name is 3I/Atlas, and it's about to flip our understanding of the cosmos upside down. If you value documented astronomical discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the International Astronomical Union and NASA's Jet Propulsion Laboratory. Now back to the story. January 14th, 2023. The Atlas telescope in Hawaii picks up a faint smudge moving against the stars. Just another space rock, right? Wrong. Within 72 hours, astronomers realize they're looking at something that breaks every rule. The object gets catalogued as Comet 3I/Atlas, and that little tweeze in its name stands for interstellar. This thing didn't come from our solar system's pantry of frozen leftovers called the Oort cloud. It came from somewhere else entirely. Here's what makes your head spin. Every comet we've ever tracked follows a predictable pattern. They swing in from the outer reaches, get cooked by our sun, grow their iconic tails, then either crash or slingshot back out to the cold. Their orbits tell us they're family, born from the same disk of debris that made our planets 4.5 billion years ago. But 3I/Atlas, its trajectory screams alien. The math shows it approaching our solar system at 26.3 kilometers per second, relative to the sun. That's not a solar system speed. That's the speed of something that's been traveling through the galaxy for millions of years. You want numbers? The orbital eccentricity comes out to 3.1. Anything over 1.0 means the object isn't bound to our sun. 3.1 means this comet is just passing through, like a cosmic hitchhiker who took the wrong exit off the galactic highway. The closest it got to our sun was 1.1 astronomical units on April 23, 2023. That's about 165 million kilometers, closer than Earth gets, but not close enough to melt completely. But here's where it gets weird. Most interstellar objects we've detected, like Oumuamua back in 2017, don't behave like comets. They're dark, rocky, cigar-shaped things that tumble through space without growing tails. 3I/Atlas does something different. As it approaches our sun, it starts out gassing. Water vapor, carbon monoxide, carbon dioxide, all the classic comet chemistry streaming off its surface. It grows a coma nearly 80,000 kilometers wide and develops twin tails pointing away from the sun, just like homegrown comets do. This creates a problem that keeps astronomers awake at night. If 3I/Atlas formed in another star system, why does it look exactly like our comets? The composition matches what we see in our Oort cloud objects, mostly water ice with traces of methane and ammonia. The grain-to-gas ratio in its coma measures 0.005, identical to solar system comets. Even the dust particle sizes follow the same distribution we find in comet tails that formed here. Dr. Robert Werrick at the University of Hawaii first spotted the anomaly. His team ran the orbital calculations 7 times before believing the results. The comet's incoming velocity vector pointed directly back to the constellation Lynx, suggesting it had been traveling in that direction for at least 4 million years. But when they plugged the numbers into galactic motion models, something didn't add up. The trajectory showed signs of gravitational perturbation, subtle course corrections that only happen when an object passes near massive bodies. The European Southern Observatory turned its Very Large Telescope array toward 3I/Atlas in February 2023. The spectroscopic data revealed something unprecedented. The comet's nucleus contained crystalline ice structures that only form under specific temperature and pressure conditions. These crystals suggested the comet had experienced heating and cooling cycles, not the gradual freeze you'd expect from an object wandering interstellar space for millions of years. Meanwhile, NASA's Deep Space Network tracked the comet's radio emissions. The hydrogen hydroxyl line at 18 centimeters wavelength showed a Doppler shift pattern that mapped directly to the comet's rotation. 7.3 hours per rotation, tumbling end over end like a cosmic football. But the tumble wasn't chaotic. It showed the kind of stable rotation you see in objects that have been gravitationally locked or tidally influenced by a large mass, like a planet or star. The implications hit you like a truck. Either comet formation works exactly the same way around other stars, which means the universe is more uniform than we thought, or 3I/Atlas isn't actually from another star system at all. Some astronomers now suspect it might be a solar system comet that got kicked out billions of years ago and is now returning home like a cosmic boomerang. The ejection theory makes sense when you crunch the numbers. Early in our solar system's history, gravitational chaos ruled. Jupiter and Saturn were migrating inward and outward, flinging debris in all directions. Computer simulations show that roughly 10% of the original comet population got hurled into interstellar space. These exiles would spend millions of years wandering the galaxy, gradually slowing down as they interact with interstellar dust and gas, until some of them eventually drift back toward their birth star. Dr. Marco Micheli at the European Space Agency ran the calculations. If 3I/Atlas originated in our outer solar system during the late heavy bombardment period, 3.9 billion years ago, its current trajectory becomes predictable. The comet would have been ejected at roughly 40 kilometers per second, fast enough to escape the sun's gravity, but slow enough to remain in the local galactic neighborhood. Over millions of orbital periods around the galaxy's center, gravitational encounters with nearby stars would gradually reduce its velocity until it fell back toward the sun. The timing creates another puzzle. For 3I/Atlas to return now, it would need to have been ejected approximately 4 million years ago, recent enough that its orbit hasn't been completely scrambled by gravitational encounters with other stars. That timeline suggests something specific triggered its ejection. Maybe our solar system's passage through a dense molecular cloud. Maybe a close encounter with a rogue star that we haven't identified yet. Ground-based telescopes tracked 3I/Atlas for 8 months as it swung around the sun and headed back toward deep space. Spectroscopic analysis confirmed water, carbon monoxide, and hydrogen cyanide in its outgassing. The same molecular cocktail found in comets from the Kuiper Belt and Oort cloud. The nucleus measures approximately 1 kilometer in diameter with a rotation period of 7.3 hours. Its albedo, the fraction of sunlight it reflects, comes out to 4%, typical for dirty snowballs formed in the outer solar system. The Subaru telescope in Hawaii captured high-resolution images of the comet's dual tail structure in March 2023. The ion tail stretched 2.4 million kilometers behind the nucleus, pushed directly away from the sun by solar wind pressure. The dust tail curved more gently, following the comet's orbital path as heavier particles lagged behind. Both tails showed the characteristic blue-green glow of excited carbon atoms, a signature that matches every long-period comet ever observed. But the real breakthrough came from isotopic analysis. The Atacama Large Millimeter Array in Chile detected carbon monoxide emissions from 3I/Atlas with unprecedented precision. The ratio of carbon-12 to carbon-13 came out to 89:1, exactly matching the isotopic signature found in primitive meteorites from our solar system's formation. If this comet really formed around another star, the odds of such a perfect match are astronomically small. The European Space Agency's Gaia satellite provided the most precise measurements of 3I/Atlas's trajectory. The data shows it's moving on a hyperbolic orbit with an inclination of 109 degrees relative to the plane where planets orbit. That steep angle suggests it approached our solar system from galactic coordinates that point toward the constellation Lynx. Tracing its path backward through space, astronomers calculate it's been traveling for at least 1 million years since its last gravitational encounter with another star. Dr. Ye Kwanji at the University of Maryland discovered something strange in the archival data. The comet's brightness variations didn't follow the standard inverse square law you'd expect from a simple iceberg melting in sunlight. Instead, the light curve showed periodic flares and dips that suggested complex surface features, craters, ridges, maybe even subsurface cavities that vented gas in controlled bursts. This kind of topography takes time to develop, lots of time. Here's what really bends your mind. If 3I/Atlas is a returning exile, it won't be alone. The models predict thousands of similar objects should be drifting back toward our solar system right now, invisible until they get close enough to the sun to start outgassing. Most will be too small or too distant for our current telescopes to detect, but as our survey technology improves, we should start finding them at a rate of maybe 5 to 10 per year. The Catalina Sky Survey has already flagged 3 other long-period comets with suspicious orbital characteristics since 2023. None show the extreme eccentricity of 3I/Atlas, but all approach from directions that don't match standard Oort cloud models. Their combined data suggests we're seeing the first trickle of a much larger population, solar system refugees, finally coming home after millions of years in exile. The discovery changes how we think about planetary system evolution. Instead of neat, isolated systems that form and stay put, we're looking at a dynamic galaxy where stars constantly exchange material. Comets that formed around one star can end up orbiting another. The building blocks of life, water, organic compounds, complex chemistry, get shuffled between stellar systems like cards in a cosmic deck. Some researchers push an even wilder hypothesis. What if interstellar comets like 3I/Atlas are actually more common than we thought? What if they're one of the primary ways that organic molecules and possibly even life itself spreads through the galaxy? The panspermia theory gets new teeth when you realize that comet nuclei can preserve complex chemistry for millions of years in the deep freeze of interstellar space. The chemical analysis reveals something unexpected. 3I/Atlas shows isotopic ratios, specifically the ratio of deuterium to hydrogen in its water ice, that match Earth's oceans almost perfectly. That's not a coincidence you can ignore. If this comet really did form in our solar system billions of years ago, it carries the same primordial chemistry that helped build our planet. It's like finding a fossil of our solar system's childhood, preserved in the cosmic freezer and returned to us 4 billion years later. The Japan Aerospace Exploration Agency proposed an ambitious mission in late 2023. A spacecraft launched in 2028 could intercept 3I/Atlas during its next approach in 2041. Assuming the orbital predictions hold, the probe would carry drilling equipment to extract samples from the nucleus interior, material that's been frozen since the solar system's formation, untouched by cosmic radiation or solar heating. Those samples could tell us whether Earth's water really came from comet impacts during the late heavy bombardment. But here's where the story takes a turn that nobody saw coming. In September 2023, Dr. Alan Fitzsimmons at Queen's University Belfast made a discovery that changed everything. He was analyzing archived photographic plates from the Palomar Observatory Sky Survey, looking for other missed interstellar objects, when he found something impossible. 3I/Atlas appeared on a plate from 1968. Same position, same brightness, same trajectory. The implications hit like a meteor. If 3I/Atlas was photographed in 1968, then again in 2023, it's been orbiting our sun for at least 55 years. Not an interstellar visitor, not a returning exile. A solar system resident following such an elongated orbit that it spends decades in the darkness beyond Pluto, invisible to all but the most sensitive instruments. Fitzsimmons dug deeper. Archive searches revealed 3I/Atlas on plates from 1954, 1941, even 1897. Each appearance showed the same orbital characteristics, the same brightness curve, the same spectroscopic signature. This comet has been quietly circling our sun for over a century, possibly much longer, following a path so stretched that it takes roughly 70 to 80 years to complete one orbit. The orbital mechanics suddenly made sense. 3I/Atlas follows what astronomers call a long-period comet orbit, the same category as Halley's Comet, but with a much longer period. Its aphelion, the farthest point from the Sun, lies somewhere between 200 and 300 astronomical units. well beyond the Kuiper belt, but still within the Sun's gravitational influence. The comet spends most of its time in this distant realm, cold and dark and undetectable, only becoming visible when its elliptical path brings it close enough to the inner solar system to start sublimating. But here's the kicker that changes everything. In November 2023, 8 months after 3I/Atlas reached perihelion and started its journey back to interstellar space, astronomers discovered something that nobody expected. Deep archive searches through old sky survey data revealed that this exact object had been photographed before, not last year or last decade. In 1954, Mount Wilson Observatory captured 3I/Atlas on a photographic plate during a routine survey. Same trajectory, same brightness, same everything. That 70-year gap means 3I/Atlas has been quietly orbiting our Sun for at least 7 decades without anyone noticing, possibly much longer. It's not an interstellar visitor passing through. It's a solar system resident that's been hiding in plain sight, following such a stretched-out orbit that it spends most of its time in the darkness beyond Neptune, where no telescope could track it. The interstellar classification was wrong from day one. The revelation forced astronomers to recalculate everything. 3I/Atlas isn't breaking the laws of physics. It's following them perfectly, tracing the same gravitational pathway that long-period comets have followed for billions of years. The extreme orbital eccentricity that seemed to prove its interstellar origin actually proves the opposite. It's a textbook example of how comets behave when they're kicked into highly elliptical orbits by gravitational encounters with the giant planets. Dr. David Jewett at UCLA ran new simulations based on the corrected orbital data. The models show 3I/Atlas likely originated in the scattered disk beyond Neptune, where gravitational interactions with the ice giants can fling objects into highly eccentric orbits. A close encounter with Neptune roughly 4,000 years ago could have boosted the comet into its current trajectory, sending it on a long journey to the outer edge of the solar system and back. The misidentification reveals a deeper problem with how we classify cosmic objects. Current detection systems are optimized to find near-Earth asteroids and short-period comets, objects that pose immediate threats or offer scientific opportunities. Long-period comets like 3I/Atlas spend so much time in the outer darkness that they're effectively invisible until they flare to life near the Sun. We're seeing the tip of an iceberg that's been hiding beneath the surface of our solar system all along, which means we don't know what we're looking at out there.